Welcome to the Lipid Maps Podcast. I'm Matthew Conroy, and I'm delighted today that we're joined by Zoë van Kemenade from Bristol University in the UK, just over the water from us here in Cardiff. Zoë, welcome to the podcast.
Yeah, thank you very much for having me.
Unlike many of the people who use lipid maps, you don't look at lipids in living organisms, but you look at lipids in rocks and sediments. So what sort of lipids do you find there, and how did they get there?
Yeah, so the type of lipids that I look at, they're called lipid biomarkers. Basically, every organism, when it dies, it leaves this molecular fingerprint behind. So for instance, in the ocean, the majority of the biomass is shaped by microorganisms. And when these microbes die, they go from the water and they settle down to the sea floor. Now, while DNA degrades quite quickly, lipids are much more robust. So these lipids, they can be preserved in these sea sediments for up to thousands or even millions of years. Now, while DNA is quite diagnostic, lipids are less diagnostic, but still you have specific type of lipids that can be linked to, for instance, a specific type of organism or to specific environmental conditions or even to distinct biogeochemical processes. So hence the term lipid biomarker. Now, an example is that the three domains of life, so eukaryotes, archaea, and bacteria, they all synthesize different types of lipids. So for instance, while eukaryotes, they have these membrane lipids that predominantly consist of sterols, the sterol equivalent for bacteria would be bacteriopane polyols. So that already allows us to differentiate between eukaryotes and bacteria, for instance. And then even
these propane polyols are C30-35 phenol derivatives.
Exactly, yeah. They're the C35 lipids, and they're in the sedimentary record. You can also trace them back as kind of degradation products, and then they're called hopanes. So another good example might be laderanes. Laderanes are these really odd lipids. They consist of these cyclobutane rings, which are basically squares. And they're synthesized by these organisms called anaerobic ammonium oxidizing bacteria. Their occurrence has never really before been seen in nature. So they're really unique to this type of microorganism. And since this microorganism lives under very specific conditions, so in an ocean that has no oxygen, anoxic conditions, we can use these laderanes to trace back these environmental conditions as well.
So if you see a laderane, you know that derived from conditions that are anaerobic.
Exactly, yeah.
So the life in the sea, either is it growing on the bottom of the sea or falls to the bottom of the sea and becomes sediment, which may or may not become rock then further down. How do you get at these lipids then? Because they're in locations that are almost by definition inaccessible.
Yeah, well, there are also very easy ways to get them, but I'll start with the marine sediments, which are a bit more difficult to recover. So what we do, we go on research expeditions. We go on a research vessel to somewhere in the ocean, and then you basically make a drill core, or we call them piston cores. So you drop this very long tube to the seafloor, and that collects your sediments. So you'll have like a meter-long tube of seafloor sediments. And then the uppermost layers will reflect the more modern conditions. And then when you go deeper into the sediment core, that will reflect like more older and older times. And then we collect these lipids from these different sediment layers.
How old are we talking with the older layers?
Yeah, you can go back millions of years with that. Yeah. But for instance, another way to do it, which is actually much more easy, is to just go to an outcrop on land. So outcrops are these rock platforms of very ancient times. So, for instance, a good example is the Jurassic Coast here in England. So the Jurassic Coast consists of these rock formations of the Triassic, Jurassic, and Cretaceous that have been, through a combination of tectonic uplifting and erosion, are now exposed to the Earth's surface. So you can just go there with your chisel and hammer, collect some rock, and you'll get your rock from the Jurassic, for instance.
So you're getting fossil lipids in the same way that I might go with a hammer and get a fossil ammonite or a fossil shark's tooth.
Yeah. So it's basically the same thing, but then the lipids are just the molecular remnants of that. Yeah.
Have you been anywhere to any really interesting places to get your samples? You mentioned the Jurassic Coast here in the UK, which I guess is not very exotic to those of us living in the UK, but have you
Yeah,
been anywhere else?
so to the Jurassic Coast, I've only been to collect some fossils myself, but no lipids. But for my work, my most recent expedition was to the Benguela upwelling system, which is this marine system near the west coast of Africa. So we went there with a research vessel. This was when I was still working in the Netherlands, to collect some material from that ocean system. Yeah.
And what can these biomarkers tell us about the planet? Besides what species were living there, is there anything else we can infer those lipids?
Yeah, for sure. So indeed, they can be linked to specific species that might have lived under very specific environmental conditions. But also the degree of methylation, or the amount of rings, or the degree of unsaturation of these lipids can also change depending on the environmental conditions that occurred at the time. So this has led to the development of a lot of different proxies to be able to reconstruct past temperatures or past pH. And we can even use lipids to trace back past atmospheric carbon dioxide concentrations.
How do you determine the temperature or the carbon dioxide concentrations from the lipids?
Yeah, so for the carbon dioxide, one way to do it is to look at lipids that photosynthetic organisms leave behind. So for instance, algae, because when algae perform photosynthesis, they take up carbon dioxide. And when they do, they have a preference for the lighter carbon. So if you have a lot of CO2 in your atmosphere, they will incorporate more of the lighter carbon into their biomass. But when you only have a little carbon dioxide in your atmosphere, they'll include more of the heavier carbon. And this isotopic signature is kind of left behind in their lipids as well. So then when you analyze the carbon isotopic values of the lipids, you can use that to trace back the CO2 concentrations.
So the lower the carbon dioxide concentration, the heavier isotopes of carbon are incorporated.
Exactly, yeah.
I guess because the bacteria they have to get what they can. They can't be fussy when there's very little of it around.
Yeah, that's the idea behind it, at least. Yeah. Yeah, I guess that's just really useful also for the issues that we're facing today with climate change, because in order to have good predictions of future climate change, we need to know kind of the relationship between CO2 and temperature. And to know the relationship between that, we need to have data. We've never before seen these high CO2 concentrations that we have now over the last million years. So in order to get data of even higher concentrations, we need to go back further in time. So for that, you need proxies like these lipids to be able to reconstruct that.
So it has a really practical application to modern climate and the direction the world is going in at the moment. So what is it you're working on specifically at the moment?
So at the moment, I am looking mostly at reconstructing past carbon dioxide concentrations using these algal lipid biomarkers. But this method is not optimal yet. There's still a lot of method development to be done. So that's another part of what I'll be looking at. Because one of the main issues is that the method has mostly been developed based on algae species that have only lived for maybe 200 million years, which seems like a long time. But if you look at kind of when photosynthesis emerged, that's already around 2.5 billion years ago. So potentially we could go back even further in time if we have the right method to do so. So we'll be cultivating more ancient algae under different CO2 concentrations and see what that does with their carbon isotopic fractionation. And hopefully that will allow us to trace back CO2 even further back in time and in a more reliable way. I also have a lot of samples from Antarctica, which I'm currently working on, but unfortunately I haven't been able to go there myself. Okay, so hopefully in future.
You avoided the cold at least.
Yeah.
Well, it's a really different subject to what we look at mostly in lipid maps. So that's been a really fascinating and brief look at the subject of lipids in geology, or geochemistry. Yes.
Yeah.
Zoë, thanks very much. It's been really good talking to you today.
Thank you very much, for allowing me to be here.
Thanks for listening to the Lipid Maps podcast. We hope you'll join us again soon for the next podcast in the Lipid Maps series.